We know that work done is equal to a force applied over a distance. We'll just use D for distance. We could use R or S or something else, but we're going to use distance in this case. That's the equivalent of a force, a mass, times an acceleration, times a distance, which in our case could be height, the height of an object. The formula for potential energy, or gravitational potential energy. Hello Fuad, if you're listening. Okay, so close to the Earth's surface, this formula here works because the Earth's gravitational field near the ground is quite uniform. So the value of gravity doesn't change too much. It's still around 9.8. But as you get higher, the gravity reduces slightly. So even up at a satellite height, it might be between 7 point something and 9. But down at the Earth's surface, it's fairly consistent down here. So we can use that formula when gravity, or acceleration due to gravity, is not changing much. Now importantly, we can't use that formula out in space, because as you get further away from a planet, the gravitational field, as you can see from the field lines, varies. It also varies if you go up a mountain. It also varies if the Earth's crust is thicker in some areas than others. You might have more gravity. The other situation where the gravity changes might be if you have more density of rocks or materials in a certain spot. You also have a greater gravitational attraction or acceleration due to gravity at that point. So that was altitude, crust, and materials that make up the crust, such as the density, more dense rock, etc. The shape of the Earth is slightly egg-shaped, with a smaller radius here than here. So R1 is greater than R2 is greater than R1. That'll give a lower level for gravity here than over here at the North Pole or the South Pole. So we can see whenever we do work, we're actually increasing objects' potential energy in a gravitational field. And we can see that from the formula, which was work equals force times distance. And we got from that formula gravitational potential energy, or gravitational potential energy equals mg, our force, times our height. This is for close to the Earth's surface, remember. If we want to go further out into space, and way out into space, and we'll come to the meaning of definition of gravitational potential energy in a minute. But if we go further out, we have work, or gravitational potential energy, increasing gravitational potential energy, equals force. Now if you remember, if we use Newton's force formula for gravitational force of attraction, we get G m1 m2 on d squared, or distance squared. You'll see R in this place sometimes, times our distance from our force, and we're getting gravitational potential energy equals, and there's a minus sign here, and I'll explain that in a minute. We need that because of a definition of gravitational potential energy. But we have the minus sign, G, one of our D's cancels underneath, so we've got G m1, m2 on distance. And the HSC formula sheet, you'll see G, M1, M2 on R is gravitational potential energy. Okay. Gravitational potential energy is defined as the force or the amount of work required to bring an object or to move an object from an infinite distance that's outside, say, the Earth's gravitational field into a gravitational field. So work has to be done to bring an object into a gravitational field. You're pushing it or moving it over a distance, so that's work. And we have this graph that explains things quite nicely. At an infinite distance, our potential energy and our negative potential energy is on the vertical scale. On the horizontal scale, we have distance. As an object comes into a gravitational field, we say it comes from zero potential energy. If it's at an infinite distance, it doesn't have the potential to fall to the planet that we're talking about. So it's at zero. As it gets closer to the surface of the planet, it decreases in potential energy. So we get a graph like this. And remember, more negative on this side here, more negative the value, further down you get here. Any work you do on an object, moving it to a further distance away, increases the potential energy, so you're getting more closer to zero. So that's because the definition is at infinity, the potential energy would be zero. You're just out of the planet's gravitational potential. Look carefully at that formula. You can draw quite a few conclusions about the attraction between objects depending on this distance between them. Whenever you move an object up against a gravitational field, you're doing work on that object. You're putting energy in the form of potential energy into that object. So to lift a ball from here up to here, you've added potential energy. Now when you let it go, the field can release that potential energy. It doesn't have to do work. The object's potential energy is released and it turns into kinetic energy, the energy of moving objects. So kinetic energy and potential energy are linked. As you move an object further up against a gravitational field, you're adding energy to it. You're lifting, you're putting work into moving it away. A quick look at an example of the roller coaster. So we have an object in the Earth's gravitational field, roller coaster here, which has potential energy. As it falls down the slope, it releases that potential energy, or it's converted, transformed is the word we're going to use, into kinetic energy. So down at the bottom here, we've got maximum kinetic energy. If it's on the ground, we're saying the kinetic energy is a maximum, the potential energy is a minimum. As the trolley then goes up the next hill, rises, the potential energy increases because we're doing work against the field, which the field is in this direction. We're heading up, going against that field, so we're increasing the object's potential energy. It's decreasing in terms of kinetic energy, so this kinetic energy it had at the bottom here is being converted into potential energy here. So we have the maximum potential energy and our kinetic energy is now minimum. There's a variety of problems you might see, but often we want to find the work done in increasing the orbit or the altitude of orbit of an object orbiting the Earth. So moving a satellite from one place to another, and it starts with this potential energy and it ends with this potential energy after we've moved it. Now we did work moving it here, but we also did work moving it from here to here. So we've done work. And that work is the change between these two in terms of their potential energy. The way we do that, we take the furthest one away, or the largest one, and we minus it from the bottom one, and that gives us our change, and we use the triangle to represent change in potential energy. So that would equal the work that would be required to lift a satellite or move something using a rocket from one place to another, from here to here.